Welcome to my advanced electronics project, which is a solar powered capacitor banked robot which tracks sunlight and conserves energy in order to move forward. Um, what I will be demonstrating here is one of the subsections of the project, which I'm hoping to eventually make this part of my capstone project because of the amount of subsystems and other things that I can learn from the project itself. So to start off with, what I'm going to be doing for the lab demonstration is I ran into a problem where halfway through the lab, before I actually had done my actual official video recording, the 555 timer, because I could not find a specific um, NMOS MOSFET, it ended up getting fried when I tried to use transistors and stuff and feeding that into the motor I found and stuff, because I was trying to give a more complete version. And as you can see here, I had some LEDs. I was just going to show some stuff. So nothing really fancy to see here, but let me go over this really quick. And then I'll show you what I did. Luckily, I did take 2 pictures, which was a miracle that I did that before it fried, because it was just nothing left on the scope afterward. Um, and that's what engineering is. Sometimes you do make mistakes. In fact, you make more mistakes than successes some days, but you find ways of working around them. So what I did here to start with is I basically used some push buttons, and what happened is, and what did happen before, is when I pressed the first one, the yellow light turns on, which is corresponding to light sensing in this case. And when I press the second button, of course, it's hidden behind this wire, but there's a little green light LED right here. And that would turn on if you press that button. And then if you press both of the buttons at the same time, it went through these 2 resistors here and then lit up this blue LED. Couldn't find a red one, but this would have represented the motor being engaged, and the green was the energy levels were okay. And this was just a pseudo way of representing the comparators and some of my other logic that I had going on in my robot design. You can see the transistor I used there to try to make it work, but unfortunately that wasn't powerful enough. But then buried under all these wires, the 555 chip is right in here. Um, so what happened is, luckily, once again, another miracle, I was able to get one good image before it fried completely. And so I was able to demonstrate that, yes, indeed, my setup will produce square waveforms. And I did, unfortunately, I didn't capture this on video, but the peaks and troughs of this do expand and collapse, which corresponds to the duty cycle, whether it being on or off, the gaps between the peaks being the off state and the peaks being the on state. And this corresponds across the scaling depending on how you adjust your resistors and capacitor ratios in the RC network, the timing network. So the first thing I wanted to show you is I'll do a little bit of a live thing here. And this is what I would have done. I'm going to have to do it virtually because now I can't actually do it in real life. But this functions exactly the same as what I did in the lab. And basically I have this pulse with modulation frequency adjustment. And then this right here adjusts the duty cycle, this knob. And then I have two capacitors, variable capacitors over here, something else I couldn't find in the lab, but these actually are used. One of them's for a coarse frequency tolerance trim, and one of them's for a more finer frequency tolerance trim. It's basically, instead of trying to struggle with the large 250 ohm resistor, variable resistor here, in the 100 K ohm resistor here, this makes it a little bit easier if you're just like a little bit off on your frequency and you're trying to hit that exact number. then you don't have to struggle all day with these knobs that are a little bit jittery. You can use these and get that value done a lot quicker and easier. So the first thing I wanted to show you is, I'll talk about the circuit really quickly. So basically, it's just have a 555 timer, and I have two of them in my circuit. One of them is more of a current. The second one is the first one, which I label as the first one, is actually a current. It basically controls the current through the motors. And the second one, which is this one, controls the pulse width modulation, which actually allows um, the rate at which the motors actually will spin and move out. It controls all that through the base of the pull down MOSFET network, which is basically just one in this case, well, two stacked on top of each other, but they're both pull downs. And so what we first started off with is I had to do a lot of reading, and I've probably spent over 290 hours. I know it's insane, but literally 290 hours plus working on this project. But basically, I put lots of notes in my, and I'll show you that in my other video later. But this right here is a capacitor. The main thing with Simulink and Simuscape and MATLAB and everything is that there's a lot of limitations, and when you're trying to merge the different programs together, sometimes you cannot, without mapping the entire chip itself individually, to actually get the different sections to work together, which messes up when you're trying to compile or even run the whole system together. So sometimes you have to run it in subsections, and this is just one subsections of many that I have working together. And I tested them all as I went, and it made thousands of adjustments until everything worked exactly as I wanted. So first here, I'm just getting this done. So first, basically, this passes this signal that is going to be generated by this network here will be outputting our pulse width modulation to our motor over here, which is basically, I just said, to our motors. And then it goes to a scope just to kind of show you the behavior. So the first thing I did is I read up on these, and I found out that you need to put around a 10 nanofarad. That's a common one on this CONT pin. And then for the threshold, there's several ways of doing the voltage dividers and stuff. I started off with just resistors, but I ended up with 3 resistors and stuff and splitting that and all kinds of stuff like that. But I wanted to have also frequency control and duty cycle control, which I didn't see anybody really doing. So I thought, you know what, I'm going to do that. It's going to be really hard, but I think that it's something worth taking a look at because it allows a lot more flexibility. If you're running your robot and there's like a sound or it's not performing well, you can adjust the frequency or you can adjust the duty cycle. And by having the freedom, it allows you more control in different environmental conditions, whether it be low light or bad energy storage. Like it takes forever for the energy to store. Maybe, to move the robot the same amount of distance, maybe there's a better frequency or a better duty cycle that will get it there easier. Either it doesn't struggle as much or it doesn't use as much energy as it's struggling. So that's stuff that I can future work on to figure out what the optimal duty cycle versus frequency range is for each environmental condition. So the first thing that after I discovered the diode method, which was I loved using these diodes like this, one in basically one of them forward and one of them reverse bias. It allows us to control basically the charging and discharging cycles by reducing the resistance one direction versus the other. It allows longer or shorter times for the capacitors to discharge, and that allows you to control the duty cycle. By placing a 250K ohm resistor up here, and the key is about these ratios and stuff. You can't just throw any old value up there. You have to find a value that makes a contributing a contributing factor of resistance or capacitance at that specific location. If it's too low or if it's too high, it can affect other parts of the timing circuit. So you have to calculate every single value. And this took hours and hours to do, and I don't have all the calculations shown or anything like that because I had to redo them so many times. But what I finally discovered was 250 was the optimal range, and I put a 1K here just to protect the incoming. Um, and I have a 4.95 volt regulated rail that I got off my main variable rail, which is coming from the solar panel. So in the capacitors charging and discharging. So I needed to have a stable way of powering all my chips and everything else, LEDs and everything else in my circuit. So what I ended up doing is breaking off a rail from that and using a chip, a buck boost converter that holds the which is just a DC-DC converter, and it basically keeps the voltage at a specified value. And what it does is it basically draws more current to maintain that voltage. So as we look down here, you also can see I put some variable capacitors here. Our main guy is in the middle, which is a fixed one. And then I used two trimming capacitors on both sides. One of them having a greater range, one of a little bit smaller range. And by using the two of them in combination, you can get right down to exactly where you want your capacitance or your resistance with all these values to be, and therefore corresponding to the correct frequency range. One thing to note, and I'll be showing you in a second. Well, let me show you these. I've already saved all these to save some time because this takes forever. But what I did is I also captured some behavior, and I'll do one live with you. These are the base performance graphs, and if you look here and you adjust the values here, the first column here is our duty cycle and our frequency. And what I did is I simply adjusted the range of the duty cycle. And as you notice that the frequency stays the same. So as the duty cycle, you can change the duty cycle without your frequency changing because the specific way I've set up the circuit. And this allows you to change from up to 97.3 down to, if you look down here, you can I got it all the way down to 70.4. But this is not even close to the amount of different combinations you can get. You can get all kinds of different combinations by adjusting them. But this is just if you just hold everything basically in the middle or off, these off, basically these turn completely off, and you hold the frequency in the middle dial. And the same thing with this would be the duty cycle in the middle dial. And the main reason is I was wanting to make sure that in the design that the target that I wanted to set was about 3,000. It was 3,000. It was 2,000 hertz. Yeah, that was what it was. 2,000 hertz, and then with a large duty cycle range for conditional environment calibrations, like I was just telling about a minute ago. And that's why I wanted it on 2,000. So basically, I centered it at 2,000, and then I adjusted the duty cycle and the frequency so that the range off that, both directions, can be adjusted from that value depending upon if the conditions change when I build the actual robot, that I'll have the actual range to calibrate it to where the optimal behavior for their motors and the ICs and everything are. That's another thing that you should do when you're building something. You always try to center your ranges and everything else in the middle, so that if there are discrepancies, you'll be able to meet them. Because if you just let it go and just put some value down, it's good. It might work on paper and it may seem good, but the thing is that value is going to be off one way or the other. And so you want to have range on both sides to be able to adjust that. The second column is where I adjusted the frequency knob here. Of course, the knob. Oh man, this is jumping around. Frequency knob, which is right here. This frequency adjust. And when I adjusted that, it gave me these different values. As you can see, once again, when you adjust the frequency, sorry, I've been sick for a week, but um, when you adjust the frequency, it also changes the duty cycle. That's one thing that you need to be aware of. In my circuit, when you adjust frequency, it does not, unlike the duty cycle, hold the frequency. I mean, yeah, hold the frequency constant. It does not hold the duty cycle constant. So as you adjust the frequencies, you can see it's also adjusting the duty cycle. So you have to move one and the other to lock it on. As you can see, as you increase the frequency, then you also are going to be increasing the corresponding duty cycle. And then, so instead of going over this much longer, I just did the calculations without actually doing the showing you the graphs, but basically just more of these graphs, these plots here of volts versus time, and which is just the modulation. So basically, there's a coarse frequency tuning. So now what I'm doing is I'm locking in on say I'm locking on I'm right trying to get 75, but at the same time I'm wanting to get 2000. So it's not like you're going to be able to get exactly what you want. But as I'm trying to get this, I notice, okay, when I'm adjusting those variable capacitors over here, which is those little capacitor tuning dials, I'm able to um, I'm able to dial the frequency closer when I just have them completely out, because adding the capacitors actually cause the frequency to go up, not down. So if it's the other way, you're having problems where you can't, when you're hitting too low, then you can throw the capacitors in, and it will increase your frequency without, as you see, without disturbing your duty cycle. So see, just like the duty cycle adjustment with the resistance, where it holds the frequency constant, you can adjust the capacitance in those spots that I showed you earlier in the circuit, right down here, right down here. If you adjust those, it holds the it holds the frequency it holds the duty cycle constant, but then allows you to change the frequency, um, which is different from this here. As you can see, the frequency is being held the same. And over here, the frequency is changing and the duty cycle, the frequency is changing, but the duty cycle is remaining constant. So using those combinations of methods, you can get your results of 2000 hertz exactly and a 78 duty cycle, which is basically perfect for what you're wanting. And some things to note is you want to avoid 100% duty cycle, because you're just then pumping out straight power straight to your motors and stuff, and that can sometimes be hard on your chipsets and stuff. So you want to kind of aim for no more than about 95% duty cycle. Frequency range for these particular motors, the optimal is you don't really want to go over, I'd say, around 10K. If you go over 10K, you run into issues, and if you go under, you get into the like under 1,000. When you start getting under 1,000 in the hundreds, then you have problems with noise, and with the really high ones, then you have problems with where it's just not, it doesn't work as well. But I can't remember exactly what I read that I know the lower one is for noise, and the other one is for, I think it has to do with, it has to do with energy loss. That's what I was remember now. the higher frequencies past 10,000, you are going to start losing energy because the pulses themselves, they're so fast that energy is going to be lost because the motors and stuff can't respond to the frequency well enough, so it just is lost in heat. Um, so why am I talking about all this? Why is it so important to be so precise? I'm glad you asked. And here's the reason. Because precise pulse width modulation timing is essential. Because it's the only controllable variable in a solar powered robot whose energy input and motor performance constantly fluctuate. By holding the pulse exact, the robot produces constant travel distances. Even as energy availability changes, the system is intentionally designed so that the distance remains constant while the time required for each pulse expands or contracts based on available power. And this was something that I came up with and realized when I was doing the distance calculations. I was thinking, how am I going to keep this thing from running off a table or going, off into a lake or something if it's outside? Or what about if the thing decides to go, if the rover decides to go 20 or 30 feet, runs out in traffic or something? And that is why every part of this design, including calculating the capacitance ratios and everything else, which I'll be going into in my other video, if you decide to watch that one. Everything has to be calibrated. You have to calculate the weight of your components, the cost of them, the availability. And if there's a single component that doesn't work, then you have to redesign the entire system. Sometimes just a subsystem, but sometimes the entire system because there's a ripple up effect and a ripple down effect. Um, and that is just one part of my project. And that's the reason why I didn't present the entirety of my project, because if I did, it would take hours and hours of time, which it's still going to. But hope you enjoyed this, and I hope to be able to show you the progress of this project as I work on it over the next year, and we'll see what this little robot can do. Thank you again, and I'll see you on the next one.